number 3 of this exam looks like another conservation of energy. We have information about a box, its weight, it's attached to a spring, initial velocity, sliding on the floor. As we look over the problem, we should get our highlighter here. Whoops. Back to there. And get my highlighter. We should make special notes. Sliding, and we're given coefficient of kinetic friction. So that should remind us we need to factor in some sort of loss. And we want to determine the maximum distance the spring will be compressed. Just to note here, we have a velocity 4.5 feet per second to the left. So it's sliding that way initially. We got our 20 pounds, we got a spring constant. So our two states are what's shown, and then the final state is when it stops sliding, its maximum distance. Alright, so we will, let's see how to draw that. Basically we'll just label this distance D. So it's going to slide some distance D. Also notice that it says it's attached to an unstretched spring. So this means that the initial stretch in the spring is 0. But we'll go ahead and write out our conservation of energy here. K0, UG 0. I have springs, so we'll do that. Work in. K final, UG final, UE final, plus loss. Alright, let's cancel or drop some things out. That's 0. We'll set a datum for gravity here. No change in elevation, so both of the gravitational potential energies are 0. Okay. So we have some initial kinetic energy. We have no initial stretch in the spring, so that one will be 0. And that final kinetic energy is 0. This is because it stops and changes direction. Okay, we will have spring energy and we will have some loss. So we have 3 terms in our equation here. So we'll have 1/2 the mass, 20 pounds over 32.2 feet per second squared. Its velocity is 4.5. That's going to be equal to 1/2 K, 65 pounds per foot, times R, we'll write it as delta X squared. Okay, so delta X is also the distance it slides. So just to make it clearer, I'm going to write that as D. Okay, and then our energy loss is going to be friction. So friction when sliding, the force is mu sub K times N. If we draw a free body diagram of our box, we've given a simple case. I guess a complete free body diagram would have the spring force pushing there. But from this free body diagram we can see that the weight and the normal force are the same. So the friction is mu sub K times the weight. Okay, E loss is the friction force times the distance. So I'm going to plug in mu sub K, 0.6, times the normal force, which is 20 pounds, times the distance. Okay, now it's just a matter of solving. Again, we'll rearrange so everything starts here, and well, I'm going to start here. So I'll have less negative terms and make this term negative over to the other side for the solver. So let's try and get that where we can see most of it. So I'll have 0.5 times 65. I'll use x for my unknown, that's squared, plus 0.6 times 20 times x. This is a quadratic equation. Okay, and then we're going to subtract off this term, minus 0.5 times 20 divided by 32.2 times 4.5 squared. Okay, 560x squared, 0.620x, 0.5, 20 over 32.2, 4.5. Oh, let's guess initial value of 1. And the solver says 0.292. Okay, so D is 0.292. The units of D, everything should be in pounds and feet for our energy terms. So D right here will need to be in feet, and D right here will need to be in feet. So it comes out as feet right here. Okay, 0.292 feet.